Greetings everybody. So we are continuing our videos on chaos-based image encryption, and the topic of today's video is going to be local entropy. Now we have already discussed about the entropy measure in our previous video. I'm gonna put the link in the comments, and you can first watch that video and then come back to discuss local entropy. So first of all, let's recap. We are talking about symmetric encryption, which means that we are using the same chaotic system in the transmitter and the receiver in order to encrypt some information, safely transmit it because it doesn't make any sense, and then reverse the process in order to obtain the original plain text back. And for this, of course, we are using the same keys on the transmitter and receiver. And we are basically discussing about the effects of two processes, permutation and substitution. Let me recap again. Permutation, or pretty simply stated shuffling, pretty much just like shuffling the deck of cards, involves shuffling the pixels of an image in order to disperse the information throughout the whole image. And the second process is substitution, in which we take each individual pixel value and we replace it with another value. And the combination of these two processes results in the final encrypted image, which is resistant to a series of statistical tests. Now, regarding entropy, as we discussed in our previous video, it's basically a measure of unpredictability or uncertainty, if you like, in a time series. Of course, in this situation, the time series is the image, and the highest possible value is around 8. So basically, in an encrypted image, we want the entropy to be as high as possible, close to the theoretical value. Okay, usually it's 7.999 and something else. Okay, here is an example of 3 different images, and the first has the lowest entropy, the middle one, the peppers, has a medium entropy, and of course the encrypted one, which looks like a completely noisy image, has the highest entropy of all. Now, as we discussed in the previous video, entropy of an image, computes the entropy of an image as a whole, as a whole time series. Meaning that the problem here is that the original and shuffled images, although they look totally different to the naked eye, but both of them have the same entropy. As you see here in the table, both of them have an entropy of 7.59. Okay, so this is a possible issue. Okay, and it's not exactly representative, right? Looking to the naked eye, we may think that, okay, why the hell does the shuffled image have the same entropy as the original image? There is explanation, of course, is because this is measured as a whole time series. Okay, so both of them have the exact same pixel value, pixel distribution, so the entropy is the same. So there is a secondary measure here that we can use in order to, differentiate between these two images. And this measure is called local entropy. Okay, what's the idea behind local entropy? I explain it here in these two images. What we do with local entropy is basically consider a collection of sub-images, sub-blocks if you like, non-overlapping in an image, okay? Much like I have here. Here, for example, I have 30 different blocks, non-overlapping, and each block is of size 44 times 44 pixels, okay? And we compute the entropy of each individual sub-block, okay? So we have 30 different entropy values, and then local entropy is actually the mean value obtained from these 30 different entropies. Okay, so you may ask, why 30 blocks? Why to the size of 44 by 44? Of course, this has to do with the size of an image. If we consider very, very large images, possibly have to take more blocks than 30. This is a common, understanding, common setup used in the literature. I will print some papers in the comments below of the video. Usually they take 30 blocks of this size, but depending on your image size, you may have to take more blocks and possibly a bit higher blocks, larger blocks. So the results are as follows. For example, here I have 6 different examples of randomly picked 30 blocks in an image. You see, I pick them randomly. I have a very simple code to perform so. It's very easy to write it in MATLAB. So in each situation, we may end up with different blocks, but pretty much the result is going to be around the same. So for my grayscale image, if we compute the local entropy, you will see that now the original and shuffle images have different entropies, different local entropies. And this is because when I pick random sub-blocks in the shuffled image, of course, the pixel distribution is heavily different. And the mean value, of course, is somewhere a bit higher than the original image. Of course, as with all situations, the local entropy, pretty much like the original entropy on the encrypted image, is the highest of all. And this actually tells us that there is a different distribution on on entropy throughout the whole shuffled image. Okay, so different sub-blocks of the image have different entropy values. Potentially here we can also take, the correlation or the covariance between the different entropy of the sub-blocks. So the same exactly thing holds with color images. Okay, here we have a technique that first of all combines all the channels together and then performs a combined shuffling process. And the idea is the same as with entropy. We can compute the local entropy of each individual encrypted channel. Okay, and I have the results right here. The idea is the same, of course, as with the gray images. The local entropy is slightly higher for all three channels. And of course, the entropy of the encrypted image is the highest of all, both for the original entropy and for the local entropy. Okay? And this is the idea behind using local entropy, and this is how it differentiates from the classic entropy, which is computed over the whole image. Okay. So thank you very much, and in our next video we will continue our discussion on analysis of chaos-based encryption.